Let's do a couple examples today related to one particular function. I'm going to define a function, I'm going to call it v, of two variables. It's a multivariable calculus function. What function? Well, I got it out of a multivariable calculus book because it's kind of an interesting function. It's going to be 4xy minus x to the fourth minus y to the fourth. We are going to relate this to differential equations and linear algebra. But before we do so, I want to think about this purely in terms of multivariable calculus. It's a function of two variables. I can find its derivative with respect to either variable. Those are called partial derivatives. dv dx, typically written with a sort of curvy d there. Is that anything magical? No, it's nothing magical. You could use an ordinary d if you wanted to. It's just traditional to use sort of a fancy looking d to indicate to yourself, hey, this is a partial derivative. This function depends on more than one variable. But when I differentiate this with respect to x, I treat the y as if it's a constant. Not too hard to do. Differentiate with respect to x, treat that y like a constant. This is a linear function of x right there, that part. Its derivative with respect to x would just be the constant, 4y. Go on to the next term, differentiate that with respect to x, you get minus 4x cubed. Go on to the next term, differentiate that with respect to x. It doesn't involve an x. It's a constant with respect to x. I'm treating it that way, at least when doing this. It differentiates to 0. That's the partial derivative of this function with respect to x. It's the rate of change of this function in the x direction, you might say, when you treat y constant. If you try to imagine the xy plane as being the domain of this function, letting x change means you're moving to the right or left, not up or down. You're not letting y change. Likewise, I can find the partial derivative of this with respect to y. Treat the x as a constant. Differentiate that with respect to y, get 4x. Differentiate that with respect to y, get 0. Differentiate this with respect to y, get minus 4y cubed. What do we care about this? Well, in terms of multivariable calculus, we care about finding max and min values, right? Just like in calculus 1. What do you do in calculus 1? You take a derivative, you set it equal to 0, you solve for x. Those are called critical points. You try to test to see if they give you local maxes or mins. There's a first derivative test. There's a second derivative test. You know, second derivative test is like, is the graph concave up or concave down near the critical point? If it's concave up, the second derivative is positive. You got a local min. If it's concave down, the second derivative is negative. You got a local max. We can do something similar here. Instead of one derivative being set equal to 0 and solved for x and y, or for x, we got two derivatives equal to 0 that we solve for x and y simultaneously. Kind of like solving for equilibrium points for systems of differential equations. In fact, yeah, we are going to relate this to systems of differential equations. Not yet. Okay, so I'm setting these equal to 0, solving for x and y. Okay, I can divide both sides by 4. I can also rearrange these equations. This equation is equivalent to y equals x cubed. This equation is equivalent to x equals y cubed. Weird. The graph of this equation in the xy plane is a cubic, an ordinary looking cubic. The graph of this one in the xy plane is a sideways cubic, actually. You'd have to graph it as a function of y. It's like a sideways graph. It would look like this. And these two graphs, where they intersect, maybe I should have drawn them in the same plane, would be the places where these two things are equal to 0. I'm going to skip the algebra. It's not too hard, but it's a little funny. You end up with an 8th degree equation when you substitute one of these into the other. Well, a 9th degree equation, actually. But there's actually only 3 places where these intersect. If you put this graph on the other one on the same set of axes, they intersect at these 3 points, the origin and the points 1, 1, and -1, -1. In other words, the critical points are 3 of them, -1, -1, 0, 0, and 1, 1. 3 critical points for this function of 2 variables. 3 places where you could possibly have local maxes or mins. Possibly. How do you decide? Is there a second derivative test for multivariable functions? Yes, there is. I want to show you that test, actually. You take what are called second order partials now. This is worthwhile. Keep this in mind for differential equations in linear algebra. Take second partial derivatives. Differentiate with respect to x twice. What do you get? Well, the derivative of v with respect to x twice is going to be the derivative of v with respect to x, and then differentiate that with respect to x. Again, treat the y as a constant. Going to get negative 12x squared, right? That's going to differentiate to 0. Negative 12x squared. Okay, in your notes, don't do what I do. Go to the lower right here and do the same kind of thing, except differentiate with respect to y twice. Leave space here and here on purpose. Differentiate with respect to y twice means now I need to differentiate this with respect to y. I get negative 12y squared. I purposely left space here and here. Why? Because I'm going to do 2 more second order partials. Wait, how could I possibly do any more? Well, back here, I took the derivative of v with respect to x, treating y as if it's constant, and got this. But hey, that is an expression that involves both x and y. I can now change my perspective and think of x and y as both being variables. And why not differentiate with respect to y? Why not? What would you call that? Maybe this? Weird. But yeah, standard notation. This is the second order partial of v. Go from right to left here with respect to x first and then with respect to y. Weird notation. Yes, I know. But that is standard. So now I'm taking this thing and differentiating it with respect to y. Treat the x as a constant. I just get 4. Right? Do something similar with this one. I guess I should switch around the x and the y on the bottom here. Second order partial, it's called the mixed partial of v, where you do with respect to y first and then x. Again, down here, this notation, you go over from right to left. I'm not explaining why the notation is the way it is. There is a logic behind it. So I'm going to differentiate this with respect to x. Treat the y as constant. I get 4 again. Is it an accident that these are the same? No, it's no accident. And why did I make it like this? Hey, that looks like a matrix. Yeah, it's a 2 by 2 matrix. Is it the Jacobian matrix? Not a V, it's not. Because the Jacobian matrix of a function, well, of really a vector field, involves first order partials. These are second order. It's got a different name. It's called the Hessian matrix. Hessian matrix of the function v. Hessian matrix. That's it. H-E-S-S-I-A-N. Matrix of v. And it's a symmetric matrix. There's one connection with what we've been doing recently. It's a symmetric matrix. It would have real eigenvalues. And the eigenspaces would form a basis for R2. There'd be 2 linearly independent eigenvectors, even if there was a repeated eigenvalue. And it's orthogonally diagonalizable. Do we care about orthogonally diagonalizing it? If we used it to create a quadratic form. Is that in lecture 30B or 31B? I forget. What's a quadratic form? You'll learn about it in lecture 31B. Quadratic form. You can treat it as a pure linear algebra topic, but it's got applications to differential equations. Is that what I want to do here? No. I'm trying to learn about this function. I'm trying to classify these critical points as maxes or mins or maybe neither. What's the quickest way to do that? Let's call this, okay, it's the Hessian matrix. Let's call it, I think I don't want to call it H because I'm going to reserve the letter H for something else here today. What should I call it? I'll just call it A. I want to reserve the letter H for something else. We can evaluate this matrix at the critical points, just like you evaluate Jacobian matrices at equilibrium points. The purpose is for something different, though actually related. So again, here are the critical points. If I plug in -1, 1, -1, or 1, 1, I'm going to get the same thing because I'm squaring. What will I get? I'll get -12, 4, 4, and -12. If I plug in 0, 0, what will I get? I'll get 0, 4, 4, 0, right? Plugging the critical points of the function v into this matrix A as if it's a function of x and y, which it is. Really, it's a matrix valued function of x and y. Weird, but true. Most important thing about these matrices in terms of classifying these critical points is what their eigenvalues are. Now, they got to be real because these are symmetric matrices. Could I use the trace and determinant to figure out them? What kind of real numbers they are, like both positive, both negative, one positive, one negative? I could. Trace is -24. Determinant is 144 minus 16. Trace is negative. Determinant is positive. Thinking about the trace determinant plane here. I'm not thinking about differential equations, but I am thinking about eigenvalues. You plot this in the trace determinant plane, it's going to be over here in the second quadrant, where for a differential equation, you'd get either a spiral sink or a real sink. In either case, it's a sink, meaning you got negative eigenvalues. You got 2 negative eigenvalues. If you solve for the eigenvalues, here you get 2 negative ones. 2 negative eigenvalues. What's the significance of that? Come back to that in a minute. What about this one? Trace is 0, determinant's -16. In the trace determinant plane, we're down there. For differential equations, that's where you have a saddle point. What about for multivariable calculus? It's still a saddle point. In a way I'll show you in a few minutes. 0, 0 is neither a local min nor a local max. It's a saddle point. I'll give a graphical meaning to this in a minute that shows you it looks like a literal saddle that you would sit on. And that's why it's called a saddle point. What about having 2 negative eigenvalues here? That's analogous in the Calc 1 sense with the second derivative test to having a negative second derivative. Concave down graph, local max. You have local maxes at these 2 points. That's the conclusion. At both of them. In fact, because this is symmetric in a sense in x and y, you get the same output. V of -1 equals V of 1, 1. What do you get? 4 minus 1 is 2 in both cases for the output of the function. At the saddle point, V of 0, 0, you get 0. What does it mean to be a saddle point? I'm about to show you. Yeah, let me show you right now. I promise I'm going to relate this to differential equations in linear algebra. I've done a little bit of linear algebra already, but I'll do even more. I've got this function plugged into Mathematica. Plot 3D will plot such a function. though it picks the scales on the axes in such a way that you can't really see the nature of the graph real clearly. If I restrict the plot range, the outputs being, say, from -3 to 3, then we can see it more clearly. Yeah, local max, high point of the mountains here, at -1, -1, and 1, 1. And yeah, some sort of saddle point. It's like you could sit on that. And it'd be like a saddle on a horse at 0, 0. It's neither a local max nor a local min. So what we've just done is we've done some multivariable calculus to understand this function better. All right, let's relate this to differential equations and linear algebra now. Particularly to differential equations. Given a function like this, there are two standard ways of creating systems of differential equations whose phase portraits are very much related to the graph of this function. Yes, this graph that I just showed you, but also, perhaps more easily to understand, the contour plot of this function. At least if I make enough contours. What are we looking at here? This graph here essentially takes this graph here and slices it with horizontal planes. And the curves of intersections that you get when you slice this graph with horizontal planes look like these curves here that you see. These are called the level curves of the multivariable calculus function. Along any one of these level curves, the function output is constant. It's perhaps too small for you to see here, but I'm putting the cursor right here and it says 0. I put the cursor right there, it says 0.33, 0.66, 0.99. Heading up toward 1, 1, there's a local max value of 2. There's a local max value of 2 here as well. The origin, 0, 0, is right there, and the output is 0. If I go down this way, the outputs become negative. Negative 0.33, negative 0.66, negative 0.99, negative 1.32. Maybe too small for you and back to see. There's two standard ways to take this graph and make, again, systems of differential equations whose phase portraits, solution curves, are going to be very much related to these curves that you see. The easier one to understand, at least at first, is the corresponding gradient system. Corresponding gradient system. Heard the word gradient before? In multivariable calculus, if you're in that class. Gradient vectors are what we're talking about here. Upside down delta. Okay, is that a triangle or is it an upside down delta? Okay. Think of it as an upside down delta. Technically, it's called a nabla because it's like a harp. That doesn't look like a harp, does it? That's called the gradient vector of the function v. What is it? It's a vector whose components are the partial derivatives of v with respect to x and with respect to y. With I hat and j hat notation, you could write it like this. In multivariable calculus, you'd probably write it like this. In this class, we'd probably write it as a column vector. I'm saying all these things are equal. They're not equal in the usual sense because they're different symbols, but they represent the same vector, just with different convention for vector notations. I hat and j hat are most commonly used in physics, right? Because it's easiest to think in terms of I hat and j hat with your pictures, your vector diagrams. This kind of thing is more typically used in multivariable calculus, just because it's a little quicker to write. And this kind of thing, a column vector is typically done in this course because we want to multiply matrices times column vectors. That's why we do it this way. Anyway, it's a vector field, really. It's a function. We could use vector plot to make the vector field. It defines a system of differential equations. We can use stream plot to draw those equations. Yes, the corresponding gradient system in scalar form is dx dt equals the partial of v with respect to x, and dy dt equals the partial of v with respect to y. Now, looking at those equations is a little confusing, right? How can a derivative with respect to t equal a derivative with respect to x? How can a derivative with respect to y equal to a derivative with respect to t equal a derivative with respect to y? It's confusing. Wait a minute. We've done this a lot, right? Our right-hand side functions usually depend on just x and y. You got to interpret it in the right way to not be confused. We're looking for functions whose derivatives with respect to t equal these functions when you plug those functions of t into them, right? That's what it means to solve a differential equation. What are these partials for this example? We already computed them. They're up there. Put these two things into a vector. That's your gradient vector. 4y minus 4x cubed and 4x minus 4y cubed. 4y minus 4x cubed and 4x minus 4y cubed. In vector form, you could write this as d vector y dt equals the gradient of v evaluated at y, vector y, if you like. These are equivalent to each other. This would be your vector field. In our textbook's notation, they call it capital F of y. It's nonlinear, right? These are not linear functions of x and y. They're cubics. It's a nonlinear system. Probably can't, and it's coupled. It's not decoupled. It's probably impossible to solve analytically. Probably. I'm guessing. We could try to approximate solutions with Euler's method. We could try to more accurately approximate them on Mathematica with ND-solve or ND-solve value. But it's nonlinear. It's probably not easy to solve this. It may be impossible. But the solutions are still understandable. We can still draw the phase plane. And again, it's related to that contour map that I showed you. How? I'll talk about it in a second. What would we typically do with this so far? We would typically, well, set these things equal to 0, draw the null lines, find the equilibrium points. Hey, the equilibrium points of this have to be the same as the critical points of the function when I wasn't thinking about differential equations, because you're still solving the same system of equations. The critical points of the function become the equilibrium points of the system. -1, -1, 0, 0, and 1, 1. What kind of equilibrium points are they? We'd have to use the Jacobian matrix, right? Linearize. That's what we've been learning about recently, mostly. I could call this more typically little f of xy and this little g of xy. What would the Jacobian matrix look like for this system? Let's write it down. Jacobian matrix. J of xy. How do you find it? The upper left entry is the partial of f with respect to x. Upper right's partial of f with respect to y. Lower left, partial of g with respect to x. Lower right, partial of g with respect to y. But hey, wait a minute. F and g are related to v. F is the derivative of v with respect to x. If I take the derivative of f with respect to x, that's the same as the second derivative of v with respect to x. The Jacobian matrix of the system is going to be the Hessian matrix of the function v. Yeah. G is the partial of v with respect to y. I'm going to get the exact same matrix. That's no accident. The Jacobian matrix of the system is the Hessian matrix of the function. Weird, but true. And it's symmetric. It's the same matrix as before. And the equilibrium points are going to get plugged in just like the critical points got plugged in before. And I could go back up here and do the same thing and call it J instead of A. And think about the trace determinant plane. The two critical points where it had local maxima are going to be sinks. Real sinks or spiral sinks, we'll have to see in a minute. The one critical point that was a saddle point is going to be a saddle point of the system. Let's use Mathematica. What do the solution curves look like? Let me call this plot 1. Let's use a stream plot and plot it on top of plot 1. Stream plot. What's the vector field? Little f is, again, 4y minus 4x cubed. Little g is 4x minus 4y cubed. Isn't that pretty? What do we see here? We see the solution curves of the system, and they do look like there's some sort of relationship with the level curves of the function v. In fact, anytime one of these curves crosses one of these level curves, it looks like it's orthogonal to it, perpendicular. Yes, that's true. The gradient vector at any point is always orthogonal to the level curve, except at critical points where you can have like the curve intersect itself, or just be a single dot at -1, -1, 1, 1. I should probably draw those in here as well. So I'm putting the equilibrium points in here. There they are. Looks like these two are sinks and this one's a saddle point, right? Just like this would reveal. And the sinks look like real sinks, right? Not spiral. We didn't see spiraling. In the trace determinant plane, we'd be more over here to the left of the repeated root parabola. Real sinks instead of spiral sinks. Can I relate this to the extra heavy duty content in the lectures and the extra reading, in particular, something called the Hartmann-Grobman theorem, stability, and hyperbolic equilibrium points? What lectures do those show up? I think it's 31A, which you may or may not have watched by now. Yeah. Okay. Hartmann-Grobman theorem here. Hyperbolic equilibria, Hartmann-Grobman theorem. There's other stuff too. Hamiltonian gradient systems show up in 32. I haven't talked about Hamiltonian systems yet. I will. Gradient systems. There's something called the Hartmann-Grobman theorem in the lectures and the extra reading. It's a very advanced theorem. I just state it in a rough way because to state it too precisely is just too hard. But essentially, the Hartman-Grobman theorem is a fancy way of justifying linearization using the Jacobian matrix and its eigenvalues to classify the critical points. The fact that you've got two negative eigenvalues at these sinks means, yeah, they're real sinks. And you got one positive and one negative eigenvalue at the origin. It's a saddle point. We've just been accepting that. That's the perspective of the textbook. The idea of linearization. It's an intuitive idea. The Hartman-Grobman theorem is a way to make that more specific, more precise. These are also examples of what are called hyperbolic equilibria. What does that mean? Hyperbolic equilibria are where the real parts of your eigenvalues are non-zero. Meaning, no eigenvalues are equal to zero or purely imaginary. And that's where linearization is valid. That's the main thing to know about the Hartman-Grobman theorem and its relationship to hyperbolic equilibria. Textbook talks about situations, examples where linearization fails. They do at least one example. Section 5.1. That's an example of a non-hyperbolic equilibrium point. So hyperbolic equilibria, none of your eigenvalues are zero, and none of them are purely imaginary. They're typical kinds of equilibrium points. Non-hyperbolic are atypical, not typical. Stability. What's stability? There's two kinds of stability. There's asymptotic stability and a little bit more general kind called Lyapunov stability. There's a real technical stuff in the lectures about that and the extra reading. You don't need to fully understand those definitions. I would encourage you to do your best to kind of understand them. More intuitively, sinks, whether they're spiral or real sinks, are stable. Saddle points and sources are not stable. What is that all about? Sinks, whether they're spiral or non-spiral, are stable, and also centers are stable, where you have like periodic solutions. Saddle points and sources are not stable. The importance of this concept, and this is the most important thing for you to know, is this. Stable equilibrium points are observable. Unstable equilibrium points are not. In physical experiments, for example. Stable equilibrium points are observable. Unstable ones are not. I'm not talking about any application here for the system. Pretend there was some application. Could we observe the equilibrium points -1, -1, and 1, 1? Yes, you could. Because you could have some initial conditions in your physical experiment. And because these are sinks, it's very likely that your solution curve would go toward one of them, and you would observe that. On the other hand, a saddle point is unstable. It's not observable really in a physical experiment, because you'd have to be exactly on a solution that heads toward it as time increases to actually observe it. All the other solutions, which are most of them, don't head towards that equilibrium point as t increases. You could possibly observe them close, but not exactly. The prototypical example to think about is a pendulum swinging back and forth. If you allow it to go around and around, so there's no ceiling up here, or it's not attached to a ceiling, so it bumps into the ceiling. It can go around and around. There's a stable equilibrium point pointing straight down, right? You give that pendulum a little flick, it starts oscillating, but then because of damping, the oscillations get smaller and smaller, and effectively, after a certain amount of time, it looks like it's stopped. You are observing a stable equilibrium point there. There's an equilibrium point that points straight up, though. However, that's unstable. because you give it the tiniest little flick and you're going to go away from that equilibrium. And you would have never observe it in real life unless you had so much damping that it was really stiff and you could make it stick straight up, right? But we're not thinking about that kind of example. You would never observe a pendulum standing straight up because microscopic perturbations from straight up would cause it to go away from equilibrium. The function v in this example for this system, v is called a potential function for the system. V is called a potential function for the system. Potential function for the system. That's kind of a strange terminology. What, is potentially a function? No, it is a function. It's called a potential function because in applications it's often potential energy. That's why. In multivariable calculus, you'll learn about, if you haven't already, conservative vector fields and potential functions for conservative vector fields. That's what we've got here, is a conservative vector field. V is a potential function. It's related to potential energy. That's what it's called. Another system, the second kind of system related to V, is called the corresponding Hamiltonian system, which the book emphasizes even more than gradient systems. I could use the same function to create a new system that would be the corresponding Hamiltonian system. That's different than this. It doesn't equal the gradient system, though it's related to it. It's traditional to give V a different name, though, for Hamiltonian systems, to call it H instead of V, because in honor of Hamilton. Wait, why do we use a V here when it's a potential function? Shouldn't we use a P? Tradition. So now I'm going to create a new system using a function that I'm going to call h of xy, but it's going to be the exact same function as v. 4xy minus x to the fourth minus y to the fourth. I'm just calling it h in honor of Hamilton. Hamilton lived about 150 years ago. Famous British mathematicians. The partial derivatives are the exact same as before. It's exact same partial derivatives because it's the exact same function. H equals v. The corresponding Hamiltonian system, however, of differential equations, dx dt equals something and dy dt equals something, does use the function h and its partial derivatives, but in kind of a weird way. The first component of this vector field is the partial of h with respect to y, and the second component is the opposite of the partial of h with respect to x. Weird, but true. So for this function, this is 4x minus 4y cubed, partial of h with respect to y, and then do the opposite of the partial of h with respect to x. So do negative 4y plus 4x cubed. By the way, I'm reminded that I forgot to put the null lines in the picture for the gradient system. I think I will do that still. Equilibrium points, set these equal to 0 and solve for x and y. Also, you're effectively solving for the null-clines. You get the exact same null-clines, actually, though which one is which is different. With the gradient system, setting that equal to 0 gives the x null-cline. Y equals x cubed is the x null-cline. Setting this equal to 0 gives the y null-cline. X equals y cubed is the y null-cline, but it switches with this one. Because these got switched, and this one has a negative sign, though the negative sign doesn't affect where the null-cline is. Because whether dh dx equals 0 or negative dh equals dx, negative dh dx equals 0 is the same set of points. So the equilibrium points are the same. The equilibrium points are still -1, -1, 0, 0, and 1, 1. But the Jacobian matrix is different. The Jacobian matrix, for this example, maybe I should use the same F and G notation as before. What I'm about to do is a little weird, but this was F before, this was G. Maybe I should be consistent here. If I am consistent, this becomes G of xy, and this becomes negative F of xy. Just to be consistent with the gradient system. I mean, I don't usually do this, right? Usually I just always call that F and always call that G. But just to show you the relationship with the gradient system, I'll call that G and this negative F. And then the Jacobian matrix becomes the partial of G with respect to x here, partial of G with respect to y, negative partial of F with respect to x, and negative partial of F with respect to y. It's just notation. Purposely done to relate it to the gradient system. I wouldn't usually do this. Now, what are those partials? They are second order partials of H. This one would be a mixed partial. This one would be not a mixed partial. Careful about minus signs here. Okay, this is kind of weird. That's not a symmetric matrix, but it does have a special form. What does it equal for this example? These two would be 4s. And let's see, this one would be, differentiate this with respect to y again, I get negative 12y squared. And this one already has a negative sign in it. So this gives me positive 12x squared, actually. If I plug in the equilibrium points, let's plug in 0, 0 first. I get a diagonal matrix. Eigenvalues are right in the main diagonal. Actually, I think I must have made a mistake. Oh yeah, there's a negative sign here. One positive, one negative. It's a saddle point. What if I plug in -1, and 1, 1? I get this matrix, 4, -12, 12, -4, whose trace is 0 and whose determinant is positive. In the trace determinant plane, I'd be on the positive d-axis where the eigenvalues are purely imaginary. And guess what? That's not hyperbolic. technically speaking, the Hartman-Grobman theorem does not apply. Technically speaking, linearization fails. Although there's a catch in this example. Being Hamiltonian, it turns out linearization still works. And the fact that the linearized system is a center still implies that these 2 points are centers. Or maybe we should use Mathematica now. Let's copy and paste this code and change my vector field to being this thing for the first component, and the second component was negative 4y plus 4x cubed. Well, look at that. That's the Hamiltonian phase plane. Look at those solutions. They follow the level curves of H. Right? H is the same as V. There's the same function, same level curves. But those follow the level curves. They're effectively on top of them. Yeah, they are. And the origin is a saddle point. And these 2 points at -1, -1, and +1, +1 are centers. Solutions circle around them. And they're periodic when they're close to them, at least. The centers are stable, though not asymptotically slow. They're not sinks. The origin's unstable. These are observable. This one's not. The extra difficult content in the reading, in the lectures, in the extra readings, are relating these ideas to flows and that kind of stuff. You need to be able to relate them to flows. I hope you still try to read them. I think it's really interesting. I'm not going to test you on the super complicated details about it. I hope you would still try to read it and try to get the basic idea and run the Mathematica animations to try to help you get the basic idea. If you want to understand fluid mechanics, it is related to fluid mechanics. If you want to understand it better. And these are just two-dimensional flows, right? In fluid mechanics, you're doing three-dimensional things, so it's even harder. But if you want to understand fluid mechanics better, you can work at understanding flows better, because that's why they're called flows. It doesn't mean the flow is realistic. It doesn't mean an actual fluid would follow this kind of flow. There are physical laws that restrict what can happen. In math, there's no physical laws going on here that can restrict what can happen in the phase plane. Okay. So all these ideas especially come out in lectures 31 and 32, but they are related to other things. In our last 15 minutes, maybe we should highlight those relationships to other things, maybe in particular more linear algebra. Examples help, but you gotta work through the examples. So let's spend our last 15 minutes reviewing the linear algebra, actually. That'd be good to do. Maybe instead of going into details here on all these things you see, let's think big picture and think purposes. Okay. So in linear algebra parts, I did talk about a week ago, one purpose is coordinate changes, right? Diagonalization. You want to diagonalize a matrix. That'll be possible, for example, when you've got distinct real eigenvalues. So the eigenvectors will form a basis. For our examples, it's mostly two-dimensional space, some in 3 dimensions. In general, the theory works in n-dimensional space. You find the eigenvectors that are linearly independent. You put them in the columns of your matrix P. It's going to be an invertible matrix by the invertible matrix theorem. Probably should write some things here. There was one thing I forgot to emphasize still with gradient and Hamiltonian, but I think for this exam, let's just ignore it. One thing I forgot to emphasize. It'll be something we'll emphasize on Friday, getting ready for the final exam. So you create your matrix P, whose columns are the eigenvectors. If there are n linearly independent eigenvectors, which will happen if you got n distinct real eigenvalues by a theorem, then P will be invertible and A will be diagonalizable. These are the eigenvectors, E vectors of some matrix A. In this most typical case, P inverse AP will be diagonal, call it D. That's how you find D. You could also find A when you know D. The P and P inverse switch around. A and D turn out to be similar matrices. They have the same eigenvalues, have the same determinant. They have different eigenvectors, though, because that's related to coordinate changes. Why do we do this? Because it helps us solve problems. It's a very, very powerful problem-solving tool. What I emphasized last Monday is that to find the matrix exponential, e to the TA, you can do P, e to the TD times P inverse. That's useful for differential equations. It's also useful for difference equations that a to the n power is P times d to the n power times P inverse. E to the TD and d to the n power are easy to figure out when d is diagonal. If A is not diagonalizable, maybe it's got complex eigenvalues, then D could be like a real normal form. I called it C in the lectures instead of D. These things are still easier to find. You can still use this approach. If A has real eigenvalues but is not diagonalizable, like it's got a repeated eigenvalue, for example, and its Jordan canonical form is not diagonal, it's got a 1 up in the upper right, this is still useful because you can still compute these things more easily. Though the P is harder to figure out. On last year's exam, I've made that as part of the take-home. Probably too hard to put on the in-class portion with the Jordan canonical form. So again, the diagonalization is a problem-solving tool. Geometrically, you are changing coordinate systems to help you solve the problem. Algebraically, you use these equations. What else do we talk about? When A is symmetric, if A is symmetric, in other words, its transpose equals itself, that's a very special kind of matrix. It means it's got real eigenvalues and real eigenvalues counting multiplicity. It turns out the eigenvectors do form a basis for Rn. And A is not just diagonalizable, but orthogonally diagonalizable. The P can be taken to be an orthogonal matrix. What is an orthogonal matrix? It's a matrix whose inverse equals its transpose, which is very nice, right? Because finding inverse, that's an inverse matrix. Let me rewrite that. P inverse equals P transpose. Finding inverse matrices in general is a very difficult thing, time-consuming computationally. Very nice if we could just take the transpose, because that's very easy. Orthogonal matrices, it'd be better to call them orthonormal matrices because their columns are orthonormal vectors, not just orthogonal, perpendicular to each other, but also normalized to have unit length. So to create the P, you have to find your eigenvectors. They're going to be orthogonal, but you have to normalize them to have unit length to make the P. So that does often involve square roots. So it's not the most pleasant thing, but at least the inverse is technically, theoretically easy to find. And these relationships still hold with P transpose in place of P inverse. That's good. Symmetric matrices are very special, but they come up in lots of applications, like with Hessian matrices. Hessian matrices for nice functions are always symmetric. I also in the lectures talked about quadratic forms. I think starting in lecture 31b. What's a quadratic form? It's a quadratic function of the variables, including, you could think of it as a quadratic function of a vector variable, where if x is a column vector, its transpose is going to be a row vector. And this kind of matrix multiplication is going to give you actually a scalar. In general, A is going to be an n by n symmetric matrix. It's quadratic forms. I haven't talked about quadratic forms here in class yet. I'm just doing it now. It's in the lectures. A is an n by n symmetric matrix. X is a column vector, an n by 1. X transpose then is a row vector, 1 by n. You can multiply all these things together and you get a number, 1 by 1 matrix. This whole thing is a 1 by 1 matrix. In other words, it's a number. In the examples we do, n is 2. And you get some quadratic function of the variables. If vector x has components little x, little y, no vector symbols, you get a quadratic function of x and y. What we're interested in with quadratic forms are whether they're what's called positive definite, negative definite, or indefinite. And that's related to the eigenvalues. If all the eigenvalues are positive, they will be real, by the way, because this is a symmetric matrix. If they're all positive, it's called positive definite. If they're all negative, it's called negative definite. If it's a mixture of positives and negatives, it's called indefinite. In the case where n is 2, you're interested in level curves of this function, multivariable calculus function, which are either going to be ellipses or hyperbolas, based on what kind of quadratic form this is, based on what the eigenvalues are. When I'm talking about that, just like I am now, that's a purely linear algebra thing related to graphing multivariable calculus functions. Can it be related to differential equations? Yeah. Your quadratic function, for example, could be a potential function for a gradient system or a Hamiltonian function for a Hamiltonian system. And then those level curves are going to be related to the phase plane. Okay, so you can apply it in those kinds of situations. Other linear algebra topics include, let's look at the PowerPoint now to end class. Orthogonal decomposition theorem, best approximation theorem, and some other theorems related to symmetric matrices, the spectral theorem, which I've already talked about to some degree. We also talked about the Graham-Schmidt process. Graham-Schmidt process, kinds of theorems on these pages here are important in linear algebra. It's not immediately clear how they're related to differential equations. You got a bunch of equations here, a bunch of statements. It's important as you think about these things to think about pictures, think about the geometric meaning of these things. I do talk about that in the lectures. What's the importance for differential equations? Is it related to differential equations? The answer is yes, but not now. If not now, when? Well, the last week of class. What are we going to do the last 2 weeks of class, or the last week and a half after this exam? The two most important things, well, the one most important thing is Laplace transforms. Chapter 6 in this book. That's the most important thing that you need to do the most computations for. The second most important thing is getting an introduction to partial differential equations. And to tell you the truth, that's probably the most important thing for your future. Math methods for physics and engineering. Do partial differential equations. And partial differential equations are, believe it or not, related to this stuff. The very last lecture before this exam is 32B, Introduction to Inner Product Spaces. A more abstract topic, it's related more to vector spaces again. You just get an introduction here before this test, so I can't test you on it very deeply. Maybe it's just the basic idea. What that does is it generalizes dot products. Inner products generalize dot products. And that, in relation to this stuff, turns out to be useful for partial differential equations in ways we'll see next week. Right? So yes, like I said, lots and lots of stuff. This is the hardest stuff of the semester because there's so much advanced stuff. I think actually the Laplace transforms gets a little easier, though they're not easy. And the partial differential equations, I'm just going to test you on the most basic aspects. Okay, so this is the hardest week of the semester, probably right now. All right, have a good day.